Well, James, it's good to see you. It's been like 3 or 4 years since we met at a coffee shop in Germany,
Yeah.
where I think
Well,
you're located, right? You're in
yes, I'm
Germany.
located in Germany, in Karlsruhe.
Okay, and I think we met in Berlin, if I recall correctly. I can't remember, but
I
it
think
was
so, yeah.
it was a while. But I was over there for another project, and I just kind of want to. Sometimes I like to lead off with just sort of a big picture question. You've spent your career trying to make software predictable enough to run inside like machines and cars and other kinds of vehicles, or other kinds of systems, I should say, that can't fail. And today we're putting millions of lines of code of software and now AI, in the current definition of the word AI, inside cars that are traveling like on highways at highway speeds. Are we building systems, in your opinion, that are safer, or are we just getting better at believing they're safer?
Well, that's a good question. It's a very tough question as well. I mean, what what we've been involved is not just making systems real time, but memory safe as well. And the reason why that's important is 70% of the errors that one sees in the internet now are due to lack of memory safety in the implementation technology. So, you know, it's easy to make things real time. It's easy to make things, relatively, let's say, um, memory safe. But to get those two things to work together, that's the challenge. And
Yeah.
we're now, we now have products not just in embedded systems, but cloud products as well, where we can really run that full AI loop, which means you have a model that you can deploy in a device. You can look at what that model does, get feedback from the model by sending only the data that's really necessary for retraining, retrain the model, and then update it again. So I think this kind of ability is absolutely necessary to have safe systems because you have many challenges when using AI in the vehicle. One is, does your model really model the environment correctly? Because basically it's a statistical model that you're talking about. It's a fancy way of doing it, but it's a statistical model. That's the first thing. The second question is, does the model react fast enough to give the answers that you need? And are those
Okay.
answers correct?
So you've
So
said
those are the things that you want to look at.
yeah, you've said a lot there, and I want to unpack a little bit of it for myself and for everybody. Let's just take the word real time for the moment, real quick.
Yeah.
It Real time does not mean real fast. In your sort of, you've been asked this probably a million times. What's your definition of real time for the average
Yeah. A
consumer
lot of people
person?
think real time is right at the moment and like you're watching a film in real time. But what we say is that's live data because it's coming directly. Real time means that you can react to something within a bounded amount of time and you know what that bound is. And that's different from the colloquial usage of the term real time. It's a very precise term that's necessary for control systems.
So
Otherwise, it's just
deterministic
live
within
data.
deterministic within some bounds. They should just have called it deterministic time or bounded time, right?
It's bounded, yeah. Yeah.
Yeah.
Bounded
Um,
reaction time, exactly.
Interesting. And also now you're speaking to AI and sort of the like the updates. I assume you're talking about like up, as issues are uncovered, updating these systems, be they vehicles or other mission critical systems, um, constantly. Like,
Yeah.
so like, would that include while they're running in the field? Like, I'm thinking of autonomous vehicles, of course. You might be thinking of those as well, and maybe other things. But like, if an autonomous vehicle is in the field, it should get its and say you have a fleet of 100 vehicles, I don't know, and you
Allison.
should be 1,000. Should you be updating them all at once? And is that kind of what you're thinking? Like you should just be constantly updating those vehicles?
I am thinking that they need to be constantly updated. You updating all the vehicles at once is a difficult proposition. So we run the loop in a way that the vehicle is responsible for updating itself. It just needs to know what stand it should have and then can request it. That means if a vehicle's offline and an update comes, when it comes online, it can grab down the new model and then go. Right.
I
But
see.
these need to be updated regularly so that you can avoid problems in the field. Now, what is the time frame in which you need to update them? Well, it's not every 2 years when a new model comes out and the old models are still in the field. You need to be able to do it on a relatively short basis, which means we're talking about hours instead of years.
Right. And regression testing is done obviously in some form or fashion before this update's applied, sort of behind the scenes, I presume.
Yeah, so we actually have a concept of deployment where the first deployment we can do, the first testing we can do in the cloud in emulated mode, and the second stage would be with devices maybe on a bench, and a third stage even with vehicles in the field before it actually gets spread out to the fleets. So in
Gotcha.
this way, you have several checkpoints before deploying into the field.
Gotcha. I want to dive into that process. I think that's very interesting. But I want to kind of also, um, this is a very nonlinear conversation sometimes, but so bear with me. But
Yeah,
because I also want to kind of get a sense of what your background has been that led you to these thoughts and conclusions, because you spent decades working on um, you know attempts to solve these problems across different organizations, and in different incarnations of languages like Java or platforms, if you want to call it, but also others. And but like you started out, I think, or you were working with data general in the earliest of days, right? Is that correct?
that's correct. I actually did my undergraduate work at Yale and was originally a physics major and got into computer science there. So I have this dual background, both is nature physical understanding along with the software development aspects to it. So I come to software development from more of an engineering mindset than many others do.
Right. Yes, yes. And me too, by the way. Less so physics, but I was an electrical engineer by training, right? And so it
Hmm.
was kind of like a computer engineer studying VLSI and coming into software from that angle. So
Yeah, very
similarly,
similar. Yeah.
understanding the substrate first, upon which this soft straight, if you will, gets gets created. But at Data General, for many people might not know, it was it's a big computer, mainframe, mini frame, I guess whatever you might call it, mini computer company.
Yeah.
But it was also featured in this wonderful book by Tracy Kidder called "The Soul of a New Machine," which is like I'm sure you've read it,
Yes, I
or
have.
and I'm wondering if you were
It's a
in
nice
it.
book.
Like,
Then. I got to Data General just after that happened. So
okay,
the group in I guess Raleigh, North Carolina, was still there, but they had already come out with the new 32-bit machines based on what was described in that book. And I was involved with their gate array group. So basically, software to support their gate array development for their machines, because there was still a lot of glue logic that was done that way. Um, Now we have FPGAs, which are, essentially very similar. But at that point, we talked about gate arrays.
Yeah. And they there was wonderful stories about sleeping under desks and how hard they were all working. And then, of course, it speaks to sort of the other competitive companies at the time, kind of like subsuming some of their market share. And it's just a wonderful story about like kind of how hard and people were working, and just um, the relentlessness and the grit and whatever you want to call it that was involved in making these systems. And yet it was just certain market conditions that sort of led the industry in a different direction. And it would be interesting to have been there at that time, I guess, to
Yeah,
see the industry change from to PCs, I guess, at some point too, and personal computing.
yeah, it certainly was a very interesting time, and they even brought out a PC-like device at the time. But it's kind of a winner-take-all industry. If you're not the first best there, then you lose. I mean, Motorola saw that with Intel and Microsoft. Microsoft was just there a little faster with the Intel-based machines, and that was picked up by IBM, and it took a while for Motorola to recover from that.
Yeah. So back then, I guess it was more first to market. I don't know if that applies as much today in the autonomy world. To some
Mhm.
extent, they're the pioneers who take the arrows, if you will. But it's because I've seen many sort of early autonomy companies who are no longer with us, right?
Sure.
Um, but maybe, yeah, I guess it was just a different era back then. Things today are moving so fast. It's hard to say who's first, and how long you can maintain your first pole position.
It was also an interesting time because you had that break between NMOS and CMOS. So NMOS had reached its limit, and CMOS had not really come out onto the market yet. So there was some companies like Symbolics and others that were doing some interesting architecture things because they could do that because they didn't have to keep up with the technology race. But as soon as it started again, they lost. So that was a time when people were thinking about multiprocessing as a way to improve computation, because there was that plateau for a little bit, and then CMOS took off, and the machines became faster and faster, and people stopped worrying about multiprocessing. That didn't come back for at least a good 15 years before people
Right.
started thinking about that again. So
And
there's
you're
these waves that happen that people forget what happened the last time around.
right. Well, you're talking too about with you're talking about this underlying sort of silicon and semiconductor technology, of course, for how to build these machines. And that is a challenge for these companies to, you're building something on a platform, and then there's another better sort of platform, if you will, or scaffolding that's come along, and it's hard for you at that point to pivot over to that because of just the change, unless you've architected yourself for that sort of resilience, because there's just the platforms are just changing. And now today with um with generative AI and things it just seems like accelerated beyond some crazy level. It's hard to keep up.
It is, but then the other thing we see is a lot of half baked solutions. Things come out, there's a hype for a little bit, and then the next thing comes out, and they forget about the last thing. And I wonder, how long does it take before there's something that's solid enough that it really changes fundamentally the way we do things? I think that process is there. I think that will happen, but we need to actually maybe slow down a little bit and finish something before we go on to the next thing.
Right. And maybe
Um,
that speaks to the world of mission critical systems more, where in non-mission critical systems, maybe it's, you're it's less dangerous, if you will, to pivot to a new platform. But if a new technology, and a new technology comes along and you want to see how you can leverage that. But in mission critical systems, I guess you need that stability because there's a lot of verification and validation involved, right? Like where
yeah, that's true. Yeah.
you have to know what it is, and if you just go to the next platform, now you're revalidating and verifying everything, and you'll never produce something safe, or you'll never produce something at all.
Well, I mean, that's at least part of the advantage of the Java technology that we do support is that it's more processor independent, so that you can write the application software without too much concern about the underlying platform, because the old APIs, et cetera, change. So this is one of the things that we offer our major customers like Stellantis, where they have many different platforms and they won't want to run the same software. And we give them a way to do that and
Yeah.
give them memory safety as well.
So what are the layers of change? I mean, there's hardware, there's operating systems, there's which Java is an abstraction around computer operating systems, right? To some extent, and hardware architecture. But then there's, I guess, are there other layers in the stack too that are subject to change? I mean, when you build an application, it's, unless you're building these stovepipe applications, you're building it on layer upon layer, and increasingly so with with today's technology. There's frameworks, there's middleware, there's all kinds of things. And I know I want to talk about like what you've been doing at AICAS, because you've developed some of these layers. Um, what kind of layers are there in a system that just change, that like the shifting sands that companies and organizations have to sort of be aware of, just beyond operating systems and hardware? Are there?
Well, I mean, there's also the APIs or the protocols that we use, but to talk between things.
Hmm.
That's another interesting layer. I mean, there's new protocols for talking to AI or giving AI the ability to extract data. There's also data protocols like OPC or MQTT or Sparkplug. But if you modularize your system properly, you can avoid you can mitigate the change, the cost of changing. For instance, we support several operating systems from Linux and QNX to VxWorks, so that we can provide the same kind of support at the application level, regardless of what the underlying hardware or operating system is. And we're looking to see how that we can do the same thing for AI models, because they run fundamentally different. They're basically a huge matrix operation, and they need certain kinds of support hardware underneath them to be efficient. But you can also look at things like reducing the data needed for each node in the module. So in the cloud, this always is usually done with 64-bit floating point, but that's a lot to do when you think you have millions of nodes in your system and you're trying to calculate the next thing. But if you can reduce that to fixed point, and the smaller the fixed point, the better. You can reduce the overall cost of that calculation. So
Right,
I think
right.
the trick is to try to use these really large models to train things in the cloud, and then distill them down into something that you can actually deploy in a device where you can actually manage the cost of the computation, which is basically power consumption and time.
So you're speaking to some of the things that you're doing too have been doing at AICAS. uh, as well, right? And so I guess I'd like to bridge the gap a little bit. Like we were just talking about data general. What were some of the things like at MIT Lincoln Labs and in academia that sort of became further foundations for your your idea and your vision for um, AICAS?
Well, I did spend 6 years at MIT Lincoln Laboratory, and I worked on two different things. One was a wafer scale integration project where I worked on computer-aided design systems, and did a lot of work in Lisp of all languages. And then I worked in a second project where we had a multiprocessor, also Lisp based system for doing object recognition. So, things like, taking Doppler data and recognizing what was in that data in terms of, helicopters or other flying objects, and being able to classify them quickly so that decisions could be made based on that. So that's a real-time sensor data problem, because the Doppler radar information comes in. You need to recognize what's there in a relatively short period of time. So it's these kinds of problems that led me down the path of embedded software and real-time capability.
Gotcha. So what was the motivation then for and when was AICAS, I guess, formed?
We started in 2001, right after the dot-com bust.
Right.
So we're still self-funded, which we probably would like to change, but that's another issue entirely. Because we need to go fast in the market, and but the original idea was to take Java, which was a memory safe language, and make it usable in an embedded system, which means changing the deployment model. So right now you put a virtual machine on and you run the program on top, but that's not as efficient as you'd like to be for an embedded system. But also the way garbage collectors are normally written, they're not real-time capable. In other words, that you have every once in a while pauses that can interfere with the real-time response of the system. So a colleague came with an idea to fix this problem, and we took that and as the basis for our Jamaica VM, which is the basis of our embedded product lines even today.
And that's the Jamaica VM.
Yeah, that's the Jamaica VM. Yeah.
Yeah. And so, without giving away any, trade secrets or whatever, but like just in a nutshell, if you're when Java programmers prior to real-time JVMs, such as yours, and when they're just creating objects willy-nilly, right? They're just kind of creating objects and then letting the garbage collector do its thing, because they were doing non-real-time stuff, right? Then we as a our company got started in 2003. Dealt with how do you get around this, what real-time JVMs are out there, but also like, are there methods for creating objects such that you can control when the garbage is, when they're, and there's no longer any references to it, when those references might be reclaimed or whatever, to free up the heap space and whatever. What are some methods for dealing with that sort of heap space management, for this is a little bit more of a technical topic, but I think for the Java programmers who might be dialed in, would be interesting to them.
Sure. And there are two different things that you can do. One is in the virtual machine itself, you can redo the way the garbage collector works, and that's what we did. We don't have a separate thread in the VM for garbage collection. Rather, we do a little bit of garbage collection work at allocation time, and we don't move objects in the VM. So if you have an object, you can be guaranteed that it won't move on you. The garbage collector won't move it out from under your feet. And that makes the access time to that object stable. And because allocation is the garbage collection work is done as allocation time, if you have a high priority task that you don't want to pay any garbage collection penalty, just don't allocate in that thread. I mean, there are ways to do that. And the other is from the application point of view that you can do things like thread pooling. Now, thread pooling has a disadvantage though, and or not thread pooling. I mean object pooling. The disadvantage is that it gives you more vulnerabilities to memory safety. It's not as bad as malloc and free, which are absolutely awful, but it's worse than in garbage collection itself. So you need to be a little bit careful about how you manage pools if you use pooling as a device.
Got it. Now this was before I presume before I guess actually it's more of a question than a statement, but this was before there were, multi-core processing was really, taking hold across, consumer and other systems, I assume. Maybe that's a bad assumption. But what did multi-core allow, like pinning of certain functions such that like in another core you could do more real-time things?
Well, yeah, you can use pinning, like if you have particular tasks that are high priority tasks, you could pin them to a processor and make sure that you don't have interrupts on that processor, for instance. And you can relegate the garbage collector to another thread, but you still have this problem that if the garbage collector moves things around, you can still have an effect on the high priority threads. And that gets you to another issue about Java as a language. We actually extended the language and refined the semantics through the real-time specification for Java. And this gives you real priorities that have run to completion semantics and priority preemption, what you don't usually have in a normal Java program. In fact, if you try to run a normal Java program with that scheduling capability, it will probably lock up because people think that, they can change the priorities, but all threads will run. And that's not necessarily the case if you have a real-time scheduling where you have run to completion semantics.
Right. Now, certainly in the automotive world and maybe in other spaces, a lot of embedded software programmers would think of C, maybe C++, I don't know, as sort of as the language to use. And then you speak of Java and it was like, and maybe this is historic, right? But you speak of Java and it's like, oh, well, that Java's too slow. It's not real time. What were some of the misconceptions or correct conceptions about that? And maybe that still persists to this day.
Well, if you take a standard implementation of Java, you're right. You have those problems.
Right.
Not so much slowness anymore because the compiler technology has become pretty good. The chits, have become pretty good, but you still have this startup issue or it takes a while to warm up the software before it runs. With the real-time specification for Java, that changes the picture dramatically, because we have real-time scheduling. We have a real-time garbage collector, so a deterministic garbage collector, so that we can make sure that the garbage collector doesn't get in the way. And we have static compilation, so we can compile Java programs ahead of time to machine code in order to get the performance out that you'd like to see without this initial warm-up phase that's typical of a JITted system.
Interesting. And so, how would you overcome those, arguments? Obviously, as a company that had and has, I guess, a virtual machine, real-time virtual machine, how do you tackle that and these misconceptions, and sort of, say, hey, this really, this will work for you, and and it'll enable you all the benefits that you get from programming in maybe even a slightly higher level Java, right? Like, because there are obviously benefits from programming in Java from those who have programmed in both, myself included. I'm sure you. You can see it's, you've got more, you had more libraries, you had you didn't have to worry about certain things, and you could focus on higher level, more complex, richer systems that you could develop with Java that would be more hampered with C and C++, not to mention the platform dependencies and issues that you would get mired in. So how do you convince folks of that?
I mean, I guess the best argument I have is we have 40 million vehicles in the field that have had zero defects
with
our technology.
With Jamaica VM.
Yes.
That's fantastic. So 40,000 vehicles with Jamaica VM. And is that running
40 million vehicles?
40 million. Sorry. 40. Sorry. Yeah. I lost a couple zeros there. I'm wanting to do that. So 40 million vehicles. Now, is that running some of the real-time mission critical things, or is it running displays? I mean,
a lot of that is displays, but we also have we have a lot of data acquisition software running. So software that has to interact with the system, collect data, decide what data is important, pre-process the data, and send it up to the cloud. So, sending up the cloud is no longer data, no longer real-time a real-time problem, but collecting the data is. So being able to get the right data at the right time when an event happens, to pull up some other data, that is that does have real-time constraints. Now we have some other applications which I can only mention in passing, where real-time is an actual part of this thing. Think like radar systems, where object recognition, or in breathing machines for medical devices. We even have some fabrication machines that use our system to run the fabrication loops. But these are they're not many of them, but they are there, and they do work.
Interesting. So for so displays and data collection, there's, I guess you could certainly see some real-time needs, but for the also, like, some of the mission, what about the critical, like, controls functions and things like that? Have you seen that, in industry much, like, for just real-time, like, PID controls, use of real-time Java, or like some of the ADAS or even autonomy functions that are a little bit further out there?
Yeah, we have seen some I can't talk about because they're
Sure.
defense customers, right?
Right.
Um, some are in factories, so like creating the springs for mattresses, the control software for that, or looking at threads and improving the quality by finding bad spots in the thread, and in the process of running the spinning machine, cutting and splicing that thread again so you have a higher quality thread at the end. Those are applications where the real-time capability is what's necessary.
Gotcha. So, yeah, so that's in the on the industrial and industrial side of the world, and I guess I led this conversation off with because I've been thinking about you know autonomous vehicles, something that I've been doing for a little while,
Mhm.
and but also ADAS and how C and C plus plus were kind of like the lingua franca for engineers developing those applications. And it sounds like you overcame some of that on the display side, in these applications, but not as much in the ADAS or the controls side. Is that do you see is there sort of a hesitancy to put Java into mission critical situations, you think, in that sense, in the automotive world?
Um, I think in the automotive world, it's more of an NIH problem
I
that
see.
the OEMs.
Not invented here for people who are wondering.
Yeah, we do very well with the customers we have, but breaking into another customer is a difficult process for a company of our size, and that's why again I think having a bit of more financial backing would make that process easier. But
Right. So what are some of the like, and then there's just the question, is Java safe, right? Like, of course, safe is a big word. What does that mean? Um,
well, I spent a fair amount of time in the process for DO 178C. Now that's the latest
can you
software
yeah,
safety standard for aviation. And we I worked on the supplement for object-oriented and related technology. And in there, we have some very good guidelines of what's necessary to certify a virtual machine for a safety critical system. And we have shown that you can use that guideline to meet those guidelines to meet the safety requirements in other markets too, like for automotive. So I don't think the issue is a safety one. Um, we have, like I said, 40 million vehicles in the field. There's been no reported defects in our part of the software. None.
well,
Um,
that's a great footprint and use case. On the safety side for verification and validate for sort of the certification or V and V. I know they're not exactly the same, although related. Um, the um, the case for sort of C and those other languages are that you can certify. I guess there's MISRA-C, and you can certify these systems um, for whatever purpose, right? And verify and validate them according to certain existing standards. ISO in the automotive world, ISO 26262 and
right.
whatever. Um, there's IEC, what is it, 61508 or something, like it's
Mm-hmm.
another one which is a parent of ISO 26262, I think.
Yeah.
um the what's involved with certifying a Java based system that's not involved with certifying a C and C++ based system, and vice versa.
So Java has the advantage that from a security point of view, you have memory safety. That means when you have an error, you can locate the error and isolate it much more easily than in C. I mean, if you have an error in a C program, you get a segmentation fault. In Java, you get a backtrace. Now, if you lose one thread in a Java program, the rest can continue to run. If you lose one thread in a C or C++ program, the whole thing is gone. So that right there alone is a huge safety advantage. And that's due to memory safety. The place where you have difficulty with a Java system for safety is not so much that the system is correct, but the fact that it can meet, whether or not it can meet the deadlines. And that's where things like the real-time specification for Java and a deterministic garbage collector come to play. Now, the thing about that is that in a certification for Java, you can certify the garbage collector once for all applications. You can't do that with the memory management in C. Every single application has to be recertified at that level. So it's a higher cost. Well, not even, I mean, that part we've actually shown how to do. We have evidence before that we can do that. We even fly in the Boeing 787, by the way. Or our virtual machine does. Then you have the libraries. And so you have all these libraries that you have to certify that they meet the standards. So the more libraries you use, the more certification work you have to do. But on the other hand, once you've done it, you can reuse them. So there's this kind of a chicken and egg thing. The initial cost may be higher, but the running costs for applications become much lower because what you need to certify after that is much less.
Right.
But you need to get over that hump. Right?
You get over the hump. So certifying the virtual machine and the libraries is something that has to be done, I guess, for these. Has there been a safety certified, JVM for according to any particular standard and like some subset of the libraries?
So we've done a safety certification of our garbage collector, as a demonstration of the ability to do that.
I see.
We have not gone further than that.
But
it's just a question of going through and doing the work. The specifications are all there; they're well defined.
Right. Well, and if you're going to do it for, I guess the question is, if you were going to do it for this C or C++ based system, is it going to be cost equivalent to what it would take to do it for like a JVM? With a subset of the libraries that would be critical. And if they're cost equivalent, why not do it for the JVM with the subset of libraries, since you're going to do that once, and then you're going to be doing this 100 times, right?
Exactly. Well, that's the rub. If you're just doing one application, it's probably cheaper to do it in C. But if you're doing 100 applications, it's cheaper to do it in Java.
Right. Because I assume it's roughly the same. Like, it's not more expensive or more costly to certify the JVM and the libraries that you're talking about, the real time for these standards, than it would be for the C and C++ equivalent for whatever that stuff is, which is going to be non-standard and different across every, presumably different platform.
So once you have a qualified VM, and what qualification means that you have all the safety documentation to include it in a full system. The certification of the system becomes cheaper because there's much less you have to do. You can really concentrate on what is the new feature for this application, because it's a much more modularly certifiable system than with C or C++. One pointer mistake in a C program can affect any other part of the system. That cannot happen in Java.
Yeah. And do you, for these certifications, is it groups like, is it TUV or TUV? I never know if it's TUV or TUV. TUV, TUV Reinhold, right? Is one of the groups. Is it like, is it incumbent upon the process to have a third party do it, or is it a self-certification process? And how much would it cost in very, very rough numbers, an organization to certify, like have certified for their suite of applications? And maybe this is not something that's easy, there's an answer for, but I'm just wondering, like, rough order of magnitude to certify the JVM and the libraries that, like, a subset of the libraries. We don't need AWT, you don't need all these other libraries. You might need the Java 1.4, say, sort of minimalist standard without the GUI stuff, or Java 1.8,
Yeah, actually, going just past 1.8, we will be bringing out a Java 17 version soon.
Okay.
You have the advantage that you have modules, and you can say, we can certify these modules, so you can reduce the effort to what modules you actually use. Now, the base module is still fairly large, but the base module is sufficient for many, many applications.
Right.
And there's a couple other modules you'd want to have for security and basically for encryption. And there you go. You have a system. In fact, our embedded agent now is an OSGI framework where the Java base and some crypto is sufficient for running most of the applications that we see in the field.
Got it. And so certifying something like that, that's like $1 million. It's like $500,000 or 10
You could
million.
probably do the virtual machine itself for $500,000
Yeah.
easily. At least ours. I can't tell you about other people's, but at least ours. Right?
Sure.
Then the libraries, I don't know. We were talking about 2, 3, 4 million. I don't know. It depends on what you actually want to put in that subset.
Right.
Right.
And then, of course, the application on top of that, which is separate. But the point, though, is that for $500,000 to 1 or 2 million, this stack could be certified, and then that's reusable across millions of applications.
Like I say, the stack would be qualified, right? Because certification is always a whole system. It's, at least in the avionics, it's always the full thing.
Right.
But anything you can qualify reduces the cost of the overall thing tremendously. So you have your operating system and the Java. People haven't certified compilers yet, which is interesting. Or they haven't qualified them. But testing becomes easy because unit testing in Java is super simple. With JUnit, you can run tests in the cloud easily, and then you have your integration tests in the end. So a lot of those tests you can have already available. You run them for your system, and that's great. And then you run whatever your application is on top, and you can do most of your certification in the cloud and then deploy it onto whatever device later to do your final integration. So the fact that you have this virtual environment means you can do a lot more in the cloud, a lot more automated than people have done in the past.
Sometimes I feel like I'm dinosauring, that's not a word, myself by even assuming that one has to certify and verify and validate, because you see all of this, these neural network based AI solutions out there, which, it's based on a probabilistic, method for determining, making decisions about perception, right? Like
Yeah.
what's a car, what's not a car. Is certification and validation and that kind of V&V just like old school? And like, cause I don't see, you know, the companies that are using neural networks for mission critical systems, robo taxis or what have you, certifying or verifying and validating the neural network systems because they're not certifiable.
They're not certifiable. No, they're not.
I mean, maybe certifiable in the psychological sense, but not. But they're not there. You cannot certify. Well, so you agree, I guess. Do you agree that you cannot certify or verify and validate a neural network based system today, like for mission
Today, that
critical?
I would say that that's the case. Now, what you can do, and one of the systems we look at is that you have a verified secondary system that watches the AI system, make sure it doesn't go out of certain bounds.
Right.
Right.
Yep.
So, and I don't know to what extent that's going to be required, because this is relatively new. I don't know, we'll have to see. But a lot of people talk about certification in automobiles, and a lot less is done than what one thinks.
Right. Oh, there's nothing done for it for certification, as far as I can tell. Which is interesting because, for years these, the auto companies were ISO 26262 this and that, and followed all these procedures, and now the software defined vehicle, it's like all that seems to like be like, what did that, are we certify what?
Yeah. Well,
It's just being ignored, right?
certainly looks that way, but I can't
Looks that
vouch
way.
for my colleagues.
Well, I like to, yeah. I mean, I'm just curious, right? I don't, um, it just seems like it's not possible yet. And so I do wonder because, we encounter these situations, right? Like these neural nets are wonderful, and and generative AI is wonderful for certain things. And we could talk more about that, but at the end of the day, the way I think it's been used, you got to wonder, well, how are you going to certify that? Can test time alone really do it? I don't know.
Yeah, but that's the reason why updatability is a key issue, because it's very difficult to ensure that you've met, you have all the information necessary to behave correctly in the field. I mean, if you
That's
just go from one country to the other and look at the sign differences, that alone is a problem here in Europe, at least.
that's
Even
right.
if you're
But as
across
you
the border with
know,
Canada.
as someone who's deeply embedded with software, it is so, you know, an update can fix and address one issue, but regress 10 others, right? That were already tested, right? Because like now you're stopping for something that you previously weren't stopping for, but now you're also stopping prematurely on the 101 highway, right? Just as an
Mhm.
example, because of a false positive that was previously not there. And so that happens, right? Like you update something to fix something, and then you've now, because there's like a million other scenarios, a subset of those are now failing, and you didn't regression test those because it's difficult.
Yeah, well, it's difficult to test, but you need to test.
Yeah. Oh yeah, you do. No, 100%. Well, that's just goes back to the neural net thing. That method for introducing updates is difficult because you can't, and it's not like you can look at these, the matrix of weights that are in neural nets and know what anything means. It's just a bunch of freaking numbers, right?
That's still an open topic. There are people working on trying to have explainability in the networks, but I haven't seen anything yet that's convincing.
Well, here's where generative AI, I think, is interesting, is in terms of explainability. If you're basically using a neural network, but you can be using it to generate source code that is readable by a human being and therefore also potentially, verifiable in some way. If you're doing it via inspection and then using other tools, existing tools, right? If you can do that versus using a neural network with just a bunch of numbers to like actually do the perception. If you use the generative AI to generate the code that does the perception, you might be able to verify the code.
Yeah, I think even then it's a huge challenge. One is the code you get out might be so complex that it's difficult to understand at all.
That's true.
And what is perception? Perception is taking inputs from the field and deciding what it is that those inputs hold. And that's a matching problem. And actually, that's the part of AI or neural networks where we've had the most success.
I know.
Is being able to recognize things. It's some of the other things that are a little shakier, and as soon as you have feedback into that in that neural network, the timing of the whole thing becomes difficult. You can do a lot of recognition activity in a one-way process, which you can bound and say, okay, there's so many steps, it takes so long, and I can recognize something. As soon as you start doing generative AI, where you're feeding back into the network, then you have this extra feedback dimension. It's basically like when you put a loop in a program, right? It takes longer because it executes the same thing many times.
Right. Well,
but what might be interesting is, we have done a lot of work with program verification, where you have a specification and you have a set of rules to say this program meets this specification. Although building that proof chain is very complex. Now, if we could use an AI system to run the proof engines to build that proof chain more quickly, maybe we could verify much more code than we could otherwise. So that there's certain combinations with AI with other techniques that could bring us a lot further.
Yeah.
Think about combining an AI with Mathematica or some theorem proving system.
Right.
And you can do interesting things because then the neural net can look at the results and feedback and learn from that.
Right. Yeah. So I want to talk about this. So the point that you made about neural networks being good for perception, because it's great at pattern recognition, and you can maybe use that to say that is a car, that is a human being, that is a child, that is a dog, that is not a tumbleweed, that's not a tree, that's not a bush, that's whatever it is, that's not a snowbank, and using neural networks to do that, right, is what some people, many organizations, certainly in the automotive autonomy space, are doing, right?
But even industrial automation, a lot of these proof systems, is the board correct? Are there no cracks in it? This sort of thing. This sort of recognition is already used fairly extensively.
Yeah, but if you make the wrong decision in that situation, you end up with a bad board, right? If you make a bad decision in the situation that I was talking about, is that a human being or is it a something else that could be a life or death situation? So what I'm wondering is, and then you spoke of this independent watchdog concept, which we're heavily involved with ourselves, but like if you have, so then the watchdog, this independent thing is going to be verified, if that's the method by which you're going to verify and validate the neural network, what it, like that perception process, what is it going to do that, because it's just going to end up potentially flagging more false positives or missing things that this other system might do, and you're going to lead to a lot of availability issues.
Yeah,
You might stop a lot, and
exactly.
yeah.
You might stop a lot.
So
And it's like kids who play with automotive autonomous vehicles where they kind of stick their hand out. Like, ah!
uh, well, so I think there are some methods, I think, on the watchdog side where you can gracefully degrade, and you can sort of I think there are methods for mathematically proving um, the safety cases that you're checking against under certain controlled situations. I wouldn't say for the robotaxi situation, which is fraught with a much more complex, what they call operational design domain. But if you have something in certain geofenced application, or a more definable environment, you have a better shot at making that watchdog useful, right?
Yeah, that's why they put glass doors in front of automated people movers at the airport,
Right.
right? So that you can't interfere with the automation.
Yeah. Well, there's that, right? Right. Yeah. Adjusting the environment as well to deal with the automation. That's interesting, because it's like, what will cities of the future look like, right? With these robo taxis, maybe
Mhm.
they should be running underground. I don't know.
That's a big uh, cost, but
Yeah. No, I know. Well, that is an interesting thing. So Jamaica VM is the real-time Java virtual machine that you had. We've talked about that. Um, and what about what I guess what are some of the other tools within the ecosystem at AICAS that you've brought to the table over the years that address some of these automation and safety and real-time problems that are encountered?
So the Jamaica VM is the very bottom of the stack, right? So on top of that, we have an OSGI framework, which enables us to update code on the fly. We can actually update code in the field by using a service-oriented architecture, and then when a new service comes in, a replacement service comes in, we can start the new service, roll over all usages to new service and stop the old one. So you can really dynamically update the system.
Okay.
Now, a lot depends on having enough computational overhead to do this, but it's from a operations point of view that works, and we can demonstrate that.
And that's not just updating configuration data, which I assume is possible, but also based on what you're talking about, but also code.
Yes. So, we in OSGI you talk about services. So you run code as services. There's a service registry, so so anybody who runs in there knows what's available and can use those services. So your application is a collection of services that work together. So it's a very modular system. So it's very easy to say, well, we need to update this one and run start the new one, run the old one down after everybody's connected to the new one, and keep going. And what it also provides is not just a service registry, but also a version compatibility matrix. So if you update a service, you know what other services need to be updated as well, what other components might need to be updated as well, which means it's much easier to modularly update your system. You don't need to do this full photo update. You can do this module at a time. And every bundle that starts is signature verified before it starts. So I have a very safe system from a point of view of somebody trying to get in and replacing code, because if it's not signed correctly, it just won't run. Okay. And that's the basis of these systems that we are now ship with our customers.
Gotcha. And that's just not updating. That's updating everything, not just like graphical.
No, that's whatever services are there.
Automation, sensors, actuators, all that stuff, right?
Yeah.
Interesting.
Yeah.
And so when, like, let's take a robotic arm. I don't know if that's an application, but like if you have a robotic arm and you update it, I guess there before that happens, there has to be some sort of verification that works. Take me through that process. Like, is that like that's that simulation / bench / field process that you've talked about before, right? And maybe you could just speak to that for a moment.
Yeah. So we now have a cloud suite. So we call it the Edge Suite.
Mm-hmm.
And this OSGI framework is the agent that runs in the device. But what you can do with the cloud suite is you can use it for development and have different pools of devices, both virtual devices and physical devices. So you start out when you're doing your software development in a virtual environment, you use other modules that are finished, and you can run these in the cloud in containers and test them out using data that you've collected already to simulate the environment. And when you've passed that test, when the basic functionality works, then you can move the next step where you may have desk-based hardware and loop systems that can be used for testing. And then when that's done, you could even have a pool of devices that are fully configured and running in a controlled environment before you do the last step. So the idea is that you have this stepwise development, and that's run by our Edge device portal. We can also see all the devices in the field. And we have this concept of the current state and the desired state. So when you do an update, instead of just pushing it out into the field, what you do is say, you tell a device, the devices what their current state is. You say, here's the new desired state. You send the desired state down to the device, and the device says, based on my current state, this is what I need to get, grabs the software it needs from a server, installs it, starts it, and does the rollover.
Gotcha.
Okay, and the reason why we do it this way is that we can always compare the known state or the current state with the desired state and know what the update status is, right, of all devices. So if somebody's offline, as soon as it comes online, it gets the new desired state and can do that process itself. You don't have to push, it's a pull process. So it's much more scalable than if you try to do this as a push process. Now you can also stage the updates in a larger fleet where you say that some of them are updated right away and others are done later. So, and this helps the development process. This helps, ensure that what you actually put in the field is verified. Because, when you go from one stage to the other, there's an approval process, and there's somebody who's responsible for saying this thing is past this gate, and we can use signatures to verify, which stage you're in.
Right. Right.
Okay.
Gotcha.
So this
Interesting.
way you have a full control of it, and this can work with the development environment that you normally use. So you still use your tools like your IDEs, et cetera. And your Jenkins or what other tools, and they dock onto this so that you have this process control. And this is a role-based system. So there's different roles, but people have this developer or tester or qualifier, et cetera. And this is necessary to be able to have a well-defined process. On the other side, we also have our data, edge data gateway, which enables us to control what data is sent up from the device and give it, decide what to do with that data, display it or store it or whatever.
Got it. Got it. So now, what are some of your uses and interests in AI these days, in these embedded systems, whatever that you're using?
So what we've done is extend our agents so that we can also manage not just Java code in that virtual machine, but code outside. So whether it's a container or if it's on an AI model or if it's an FPGA program, we can model that as if it were just another bundle in the system, which gives us the full registry and versioning, et cetera, that was required for maintaining a modular system, but extends that outside the pure virtual machine. But then you can use the virtual machine to orchestrate models with other parts of the system so that you have a full system. Because just running an AI model is not enough. You always need glue code. You always need access to sensors, et cetera. So
So
this is a way to be able to pull it together.
are you saying, when you say updating AI, like an AI model, so like the actual, new sets of weights and what have you
Exactly.
get pushed to this? Now, some of those can be quite large, right? I mean, depending on the complexity of the system.
Sure. That's true. Although what we're seeing is that instead of having one huge model that does everything, you have models that are dedicated to certain functions. So each model can be smaller. So you have one for perception, another for deciding, how the vehicle should move, et cetera. I mean, just like in your systems, you had different aspects of the system that was modular, where you can do the same thing with AI models, not just put everything in the same model, because we see that one large model doesn't work as well as several dedicated models.
Oh, for sure. But so that's more for the the traditional use of, or not traditional, but the use of neural networks, for pattern recognition and like whatever convoluted neural networks, and for image recognition and things like that, as opposed to these LLMs. You're not talking about updating those kinds of models, or are you?
Well, I mean, yeah. So you need to have, if you can run an LLM in a car, you need to have enough compute power to do that. So that's a challenge right there. But even still, if you're just updating the weights, it's a lot less than updating the full
Sure,
model.
sure.
So you have savings there, and being able to do it is key. And you could say, well, you have to wait till the car's in the garage and you have a Wi-Fi connection to do that. There's ways to manage not just what gets updated, but also when. right?
Right. Right.
So that you have sufficient bandwidth to do the job in a reasonable period of time.
Right. Right. And I guess I was just getting at, like, if you were getting into the world of updating LLM models, you know, remotely. But yes, it doesn't necessarily have to be for automotive, but for other applications, given your platform goes beyond, um, the automotive world.
Yeah, automotive is our biggest revenue generator at the moment, but
Okay.
we have systems in avionics, defense, industrial automation, and medical devices,
Right.
breathing apparatus.
So so you are still fully on the Java train, right? You haven't sort of, I guess, with some of these things, have you all, um have you been leveraging like other things like Python, Rust, and C and C++ to, at any significant level, or is it pretty much focused on the Java based
Well,
platforms?
so for our internal development, of course, we use C at the very lowest level in the VM, but we do a lot of things in Java just because it's quicker and safer. But for the applications, our customers can decide what technology they want to use, and a lot of the neural nets rely on Python to run them. We're seeing some movements in the Java community, but we we can manage things outside the VM, so it doesn't really matter. Some critical things that are very static, you might want to do in Rust, like your MQTT broker. But in general, we have the most flexibility and the most safety using using Java as the implementation module, and it's faster than Python, which is another
Right.
quasi garbage collected language. And I say quasi because they keep throwing a lot of C code in there to get performance. So it's kind of
Well, it's also, I
a little bit
guess
of
maybe it's a little biased, but, Java just lends itself to more object oriented and component based. Oop,
sorry.
no worries. Java seems to lend itself to more object oriented component based programming, which allows for scale, in my opinion, versus, I mean, I, it just seems difficult to stitch together a bunch of Python.py files,
Yeah, yeah,
and build. I mean, I know people built complex things with it, but it seems a little more fragile,
yes,
uh,
yes.
from a production standpoint.
And we've done well with Java in the field. The success rate has been very high.
What's the
Which
future of Java? I mean, like, Oracle took over, things changed. Um, some of all the folks that we probably mutually knew left. And what do you think the future of Java is here? Like, it doesn't seem like Oracle's really interested in the embedded, or will ever be interested in the embedded world.
they're not.
Um, yeah.
Um, and they're moving in a way that's a bit more dynamic than I would really like. So a lot of that stuff we can mitigate with compilers, static compilers. That's one of the challenges of moving to 17. But I really think it's time for a new virtual machine.
Like a replacement for Java.
No, for the virtual machine,
Oh,
not the
okay.
language, the virtual machine.
Okay.
Because this invoke dynamic and var handles and method handles they have in there don't fit well with the virtual machine itself. So there's a lot of extra work that needs to be done to do things that would be simpler if we had virtual virtual machine support for things like tail calls, first class functions, so methods. They're not first class in the VM. Every time you want something that looks like a function, you have to wrap it in a class. And the other thing is vector operations. If you had vector operations at the VM level, that you could do a lot more. So right now we take bytecode as our language for our static compiler, so we can compile anything that goes to the Java bytecode. But if you extended the bytecode language, then you could better support other languages like Scala and some functional languages.
What JVM version would you say is the highest version that one in the mission critical embedded world should use, and don't go past that at this point, given the complexities that might have been introduced?
Well, I'd say 17 because that's what we're going to support. But
17.
No, 17's a reasonable choice still. 21 adds, so I think it's 21 that adds continuations, and that's going to be a little bit trickier for us. There are some vector stuff that might be interesting. It's hard to put a solid line on that, but
Yeah,
I think right now 17 is probably a good place to be for embedded code. And we'll have to see how it goes. Right?
And but also, are there features within 17 that you would just say should not be used for embedded real-time stuff? So while 17 may be the version limit, are there certain things that have been introduced that you're like, these do not recommend?
That's lambdas are certainly challenging, and you shouldn't use them if you don't have to.
Right.
There's a tendency for programmers to use them just because they're there.
Yeah.
There are certain applications where they make sense and could be used, but I wouldn't overuse them just because the overhead of a lambda with the current virtual machine technology is very high.
But no problem with generics and annotations, I take it.
The annotations and generics are fine.
Yeah.
They're not a problem. I mean, in fact, they could help with your code because annotations can be used to support the verification process. And
right.
I wish they were a little bit more flexible than they are, but that's the way it is.
Right. So it's kind of a management problem that I'm sure you and I have both encountered. You're an embedded Java company. You're using it to create these mission critical systems. You hire a new Java engineer, and they want to use the latest, greatest thing. And it's like, because for the longest while, I will tell you, we were like strict, well, I don't know the longest while. For a while, we were strict 1.4. We don't want to go above that because we know it. And it goes back to, this is what we know. We know it works. We've analyzed the, how it all works. And of course, we used Jamaica VM. It's a wonderful real-time Java virtual machine. And that was compatible with us. But then also, then there were some things that came along, and like the generics, and then we started to creep up to 1.8, and but like there's still some things in 1.8 that we would just be like, let's not go there. I mean, I try to even avoid nested. I don't even like nested classes, right? So that's just
Oh,
maybe it's a
that's pretty hard.
I know it's a personal
I used
thing,
to love,
maybe.
actually they're good for some things in terms of, keeping things local.
Right.
And now they have the concept of hidden classes, which reduces some security issues that were associated within their classes.
Right.
So
I think it was the readability back in the day that I didn't like. I'm like, let's just objectify everything. I'm not saying it's a good position to have. But
yeah, not anonymous classes that are created on the fly. They're
yeah,
there are places where they make sense, but again, it's like garbage collection. Don't overuse allocation. If you don't need to allocate something, don't.
right.
Decide before,
Right.
not afterwards.
Right.
Allocating something, decide that you don't need it and throwing away is not a good idea, right?
But
Well, like the other features.
the perspective of a new engineer at the time might have been, well, because this guy has gray hair. You've maintained your nice shade of hair there, but I've got the
It's
grays.
starting to go here.
But this guy, they would say, is just living in the old days. And I'd be like, look, I love the new stuff just as much as you all, but we're trying to make systems that we can verify, that we can prove work, and we don't know what the effect of some of these new things are going to be until we really test them out. And so, but yeah, it can be a battle. And so when these JVMs march along, and now you have folks wanting to use the latest greatest, that could be a challenge. And there's not sort of a someone at Oracle now, someone stewarding Java per se, seemingly saying, for those who want to use embedded, you're really like, as a company, like a standout in that regards. But there's not on the industry side, at least what I've seen, anyone sort of saying, here's like the embedded envelope that we should stick to. Like even when there was J2ME, right? Like that was at least, representative of some envelope, a boundary
Right.
around, the embedded Java that you might use, even though it wasn't specifically geared for real time or anything. But anyway, so do you think so what do you think about like things like Claude Code and these new AI code generators, if you've had the chance to kind of look into them much, or they're always moving so fast, and what that means for the future of the immediate future, not just like the distant future, but the immediate future of Java, Rust, C++ programming?
Well, I think you always need a base system to work with. The AI doesn't do everything, and it's just too inefficient to do many tasks, right? Because compute power necessary to do tasks is much higher if you solve it with a neural net than if you solve it practically any other way.
Well,
It
and
can do.
I'm not talking about neural nets I'm talking about using Claude. Claude Code generates code, right? Source code for you.
Right, and those are tools that we would use, and we do use such tools. But you have to bear in mind that they don't give. They are good at reproducing tasks that have already been done. They're not good at creating new things. You need engineers that understand their state of the art to really come up with new and better systems. If you're just reproducing, saying, "Oh, I need this thing," and I can specify it and tell Claude to do that, works pretty well. But you can't say, "Oh, take this compiler and rewrite it in Java or in Rust," or you'll get something that won't work the first time. And I think we're going to be a long while. We're still going to be some time before that works.
Well, it
And you
might not
still
work the
need
first
to,
time, but nothing we do as manual, from a not I'm not sure I've written much code that's worked the first time, right? It takes iteration for sure, right? At the human level as well as the machine level.
right. And that goes back to the whole issue of, combining these tools with other tools so that they can do a better job, right?
Yeah.
But still the aha effect, um, you know, to do something fundamentally different, you need a human in there to guide it. This will make your developers more effective, but I don't think it'll replace developers in the near term. So you'll still need languages. I mean, even these codes develop to a language. I mean, in some sense, Java is a better deployment method for these than C and C++ because it's easier to test and get the feedback you need to have an end product that's good. And the system doesn't have to worry about running out over the edge of arrays or this thing. Those things can be tested easily. So you can run this loop. They talked about vibe coding, for instance. Well,
Yeah.
if you use that to Java, it's a much easier process than if you try to do this to C or C++ or even
But
Rust.
but here's what's
because they're less forgiving.
yeah.
They're, you get less feedback from the system of if it's working right or not. But yeah,
Here
we use these tools,
here's what's
of course.
interesting. It goes back to constraining like you can tell these tools, this is what I want the coding standard to be. And
Mm-hmm.
also, I don't want you to use the latest Java. I want it to be Java 17. And I don't want you to do this, that. I don't want you to use lambdas or whatever. You can tell it that and it'll do that. Right.
Yeah.
And like, so that's interesting, right? And that it can enforce sort of from an embedded programming standpoint, it can enforce standards, right? Like that might be otherwise more difficult to enforce, with just sort of a piece of paper.
You can also say, oh, take this code and reformat it with this coding standard, and I'll
There
do
you
it.
go. That's right.
You
That's
know,
right.
and save
That's
you
right.
time.
That's right.
But if you, as a software developer, you need to be better at specifying what the code should do.
Oh yeah. That's
Because
right.
if you can specify it well enough, then the LLM can do a decent job of creating the code. If you don't specify it well enough,
Well, that's 100% accurate. And therefore, your ability to articulate um, is very important to articulate ideas and precisely, correctly, completely is important, which is a skill that's not taught in engineering schools very often.
yeah. Yeah.
So, everybody had to take a humanities class when I went to school, but I did enjoy reading the occasional Hunter S. Thompson novel. So maybe I was a little different.
Well, I went to a liberal arts school, so
Oh, there you go.
so there you go.
Um, well, what do you
Um,
think? Sorry, yeah, you were going to say?
I think the other issues you want to make sure that what you give as an assignment is small enough that you can get it, understand the results and put things together. So if you can break down the problem into smaller pieces, you'll be much more effective using something like Claude than other ones.
Right, for sure. Yeah.
Right.
So just like some sort of like final reflective, maybe even some predictive things. Like you've um, been broadly and deeply involved in this sort of embedded um, development world, which is, of course, of tremendous interest to me, and because it can be different than just programming for a server and a back end web system, whatever. It's just a different method of development, and because you're paying attention to certain things that are mission critical, and memory and processing power, and things that a lot of maybe some software practices take for granted. But what are you seeing in this sort of world? Are there any cycles that you're seeing in sort of the evolution of embedded systems development? I had someone tell me at one point, when I talked about real-time programming, they're like, well, the processors are getting so fast that you don't have to worry about determinism, because it's just going to be so fast, and it's going to be able to meet the deadline that you need, that like determinism is an afterthought, because everything's just going to be fast enough. And I'm like, well, I don't know if I have an argument for that. But because I'm not, yes, I can see that machines are going to get faster and faster, but like, is embedded development always going to be a thing, or is it going to be sort of overcome by events in the world of just faster processing power and AI and what have you? What are your thoughts on that?
Well, there'll always be a difference between OT systems and IT systems. So operational technology versus information technology. Information technology, you don't care about as much about, the time it takes. You care about the correctness. And even then, not so much. Whereas in an OT system where you have a control system, you need to make sure that that control system works not most of the time, but all the time. So what it means is, if you don't pay attention to these things, yes, it'll work most of the time, but it'll be much harder to find out why it failed in that one time, because you didn't do the right thing.
I want to take what you just said. I'm going to create a frame for that. That's like a slogan. I'm not just telling you that. That's a perfect way to describe this. And just, I want to pause, because it speaks to something that I see on the autonomous vehicle industry. You have an AI space. Folks come in from different worlds, of course, which is great. Different programming paradigms, right? And then they're trying to apply these paradigms from maybe the IT world to this OT space, and then but like these concepts that we've talked about here today, verification, validation, certification, just are not even considered. And I guess that worries me.
It worries me too. I mean, there's a protocol for AI systems to talk to one another. Now, this is a new protocol, right? And okay, it works, but there's no security in it. There's no validation in it. And these are things that we have other protocols already established that do. And you could have just adopted like MQTT, for instance, as the intermediate protocol with a protocol on top of it, and have those things. No, you have to start again from zero, make the same mistakes again. And this is part of what I'm seeing in the AI world. If we need to learn from the mistakes we made and not make them again, we need to evolve our technology, and not just, okay, everybody throws a new thing on the thing and start from scratch. And I think I'm seeing a little bit too much of that right now.
Yeah.
And that worries me.
So what would be your advice for, new engineers entering the space today, building safety critical, mission critical systems, for what tools to use, what to study?
Yeah, I think, the fundamentals of computer science are still important. What is calculus? What is the order of effort for this algorithm? That's still important. How long does your code take? What do you need to do to make sure that it can complete on time? But you also need to understand neural nets, this new environment that's coming up, and you need to understand the specification process. What does it mean to write a good specification so that you can verify that the system does what it's supposed to do and not something else? So, you can't throw out the new old, but you need to understand the new.
Yeah.
And if you can't do both, you're going to be lost. Because you can't write, you cannot just let the AI, artificial intelligence systems do what they want. You need to have them under control, which means you need to understand the problem you're trying to solve.
Right. I've seen a little bit of that with use of these tools, that you kind of get led on to this, you're generating code, and it's such a rapid process, by the way. Like, it's extraordinary. You generate all this code, and then it's like, oh, that's not quite what I want. And then before you know it, you're down this path, and you're like, this isn't really where I wanted to be, and then you kind of got to rewind and start all over, because it can lead, it happens so fast. It's like you're able to generate code faster than you can, in some cases, think about what the architecture should really be.
Yeah.
You see what I'm saying? Like, you may have because as you know, when you're building a system, you go in with a starting concept of an architecture, a design, but then that, as you discover things, that evolves. But when you're generating code so fast, it's generating it faster than you can, in some cases, evolve the architecture. And it's scary. So you end up with a little bit of a Franken system at the end.
Well, you probably need to do more of throw it away and start again.
Yeah.
Because the generation of code becomes less expensive, you can do it more often. I mean, the value of the generated code will have somewhat less value than before.
It's true. It's true.
The architecture will have more value. But, don't change the running system. If you have something that works, use it as a module and build on top of it. Don't replace it and start from scratch if you don't have to. So
yeah. Well, you can use these tools to look at your existing system and tweak it, but I think it's a little harder than starting from scratch, of course, with these AI tools. But you can certainly have it look at your system, and of course you have to set it up such that it's not training your model with your valuable IP.
Well, yeah, that's the other issue,
Yeah.
as a software house, how do you manage your IP
Right.
and take advantage of these tools at the same time?
That's right. That's right.
It's a little bit tricky.
I have some thoughts there because I've been doing it. I'm happy to share with you. But I guess just one kind of like last question for me to you is, thinking about, like, starting from scratch. If you had to, like, what would you build like right now new, if you were starting from scratch today, with without like some of the existing things that you have at your disposal?
What I'd probably really like to do if I had an open slate is build a new architecture where garbage collection is part of the architecture and matrix multiplication as well, so that I can join a system that's both memory safe with something that can work with advanced AI technology and build on that.
Interesting. Well, if you don't have time to do it, you could just ask Claude Code to do and see what it comes up with. But no, interesting. That's a very interesting concept. Yeah, fusing the two. I don't see, I don't know what's going on as much in the Java community today, as I once did. But I don't know if there's any standards afoot to sort of bridge the JVM with AI more.
They are doing things, and that's why
Okay.
I'm keep watching what they're doing. Some of the foreign interfaces look promising, at least. the question is always, how does this affect the garbage collector? The more you can do at the Java level and directly feed a model, the better, just because of that memory safety issue. But I do think a new virtual machine would help a lot, because they could take a lot of the what they have to do over invoke dynamic and make it part of the base machine.
Yeah.
But I don't know if they're interested in that.
Well, you mentioned OT, IT, and I know this isn't a thing, but R&DT, like the R&D world and like these frontier AI labs, they're all using Python, right? It seems, right? And so you've got all these Python libraries for machine learning and AI and generative AI. And it's like, if you're like, oh, I'm gonna learn how to do this, you're looking at all that, right? But to me, none of that has that OT scale that Java has. And sort of fusing those two paths, I guess if there's, I don't know if anybody's working on equivalent libraries on the Java side that could be leveraged, but and I know
There's
you
work
could.
in there.
Okay.
There's work, but it doesn't have the same traction for some reason. It seems to be easier for people to throw something together in Python, even though the semantics is absolutely terrible. I mean, you worry about indentation in your code. I mean, come on.
I know.
That's back to Fortran. Come. And I think that's the problem, is this it's easy to do it fast, but if we're going to use an AI to do it, well, maybe you could do a lot more in Java. Maybe we should really consider leveraging the AIs to build some of these libraries for Java, so that we can do it there instead, because the actual implementation, the actual runtime, would be much more efficient, because Python is
well, I mean, the problem is things are happening so fast in the AI space that, like, as soon as you do something in Java that's equivalent, now there's a new library. And so I guess Java.
You have to do the new library. That's the thing. You need to find the next best, the next newest thing, and do it in Java. That's
or I guess Java to Python bridging in the meantime.
Well, that's what we do with our systems. Is we can use the Python on the device if we need to, but we also have some flexibility, or we'll look at flexibility to take something that was done in Python and just move it over to Java.
Yeah. Well,
but we don't need to run things in the virtual machine, so it's okay.
Right. Well, James, this has been a hugely fascinating conversation for me. I'm so glad we caught up too on the state of real time and non-real time, not Java and AI and the fusion of all that, and the stuff that you're doing, the amazing stuff that you've done with Jamaica VM and AICAS. I've obviously been a fan and a user of it, so I appreciate your time here. Is there anything else you'd like to kind of like highlight that we didn't talk about?
Well, it's not just a question of technology in the end. It's a question, can you solve the problem? And I think one of the biggest challenges now for the AI world is, how do you deploy these things in systems? And this is what we're concentrating on right now, is if it's Python or Java, it doesn't matter, but actually getting it into the devices in a way that you can close that loop, or you can monitor the AI system, feedback the data that's necessary for improving the model, and then updating the model. And we have the capability to do that. And we're working with an NXP to demonstrate that, and maybe it would be nice to show you what we do sometimes, so you can get a better feel for what are we talking about with this AI update loop, and really having a full-fledged AI or ML ops for embedded.
Right. Well, I'd love to see that sometime. Yeah, we should set up a time to do that. I could do an extra add-in for this episode, downstream.
Okay.
Well,
And,
thanks.
you're welcome to come visit us anytime. I'd love to see you here.
I would love to. I'm looking to get back. I had such a great time when I was in Germany, and I have fond fond memories too of being there. And I got to visit like this castle from like I think they said it was like from the 1300s or something. I was just
Mhm.
amazed. It was just so beautiful. So I'd very much look forward to coming back and spending some more time there. Well, until then, thank you again. Thank you for taking the time to talk to me here, and appreciate what you're doing.
And thank you for taking the time to talk to me. It was my pleasure.
Thanks, James.